All right, hello. Welcome back to some more Kerbal Space Program. CheersKevin here, and today we're going to fix two bugs and land on the moon. You know, as you do. And the first bug what we're going to fix, these two bugs, by the way, are things that you found and made note of in the comments on the previous video. Unfortunately, because of the way that we changed our strategy for finding the closest approach, there are some consequences that we didn't consider. But let's get into the first one. The first one is from Nug, and it actually has to do with the position at function that we get from KOS. Now, I'm not sure if this has always been the case, but it is certainly the case now. And Nug pointed out this error and also wrote a little script that demonstrates the problem. I'm going to go ahead and turn RCS off here because I have this running. And you can see what he set this up to do is to draw these vectors as we advance time. So he's adjusting the position at over time as we're looking further out in the future. And you'll notice something interesting, and that is that our future ship is orbiting Kerbin, but the future position of Kerbin, well, it's going out being fancy over there outside of the sphere of influence. In fact, it stretches outside of here. In fact, the vector doesn't, I don't think it renders outside of the sphere of influence, so it's not particularly helpful. But the point being that if we try and use that to determine our apoapsis, well, we're being a little, we're getting a weird value, because when you're using position at, it seems to only be computing this relative to the thing that the object is orbiting. So if I ask for the position of Kerbin in an hour, it's going to tell me the position relative to the sun, or Kerbal, or whatever you want to call it. If I ask for the position of the ship, it's going to give me the position of the ship relative to the body that we're orbiting, which in this case happens to be Kerbin. So here's the script that Nug sent over. Thanks very much for that. What we actually have to fix is here when we are calculating our altitude at, what we were doing is we were saying, look at the position of the ship at a time, subtract it from the position of Kerbin at a time. And because the position of the ship at the time isn't also taking into account the rotation around the sun, we're getting bad values here. And in fact, he suggested this may be why we had issues trying to do hill climbing for finding altitude. I'm curious as to, I still don't understand why it happened to work when we were doing our ternary search, but I'm glad that we get a chance to fix that up. So the way that we can fix this is we can actually get a suffix off of orbital bodies, and that is altitude of. And what we have to do there is just pass it a vector position, and it will give us the altitude at a given position. So rather than creating some vector and getting the magnitude of it, we can just put the position at of the ship at a particular time and return that value. So we're still getting the altitude. We are adjusting the position of the ship along its orbit. We don't care that we're orbiting the sun in that case, because we don't have to measure Kerbin's position relative to anything, because we're using this altitude function instead. So appreciate catching that. I'm very confused as to why it didn't break in our test case. And yeah, it's an interesting thing to to realize. One other quick thing to note here is that we seem to have the same bug in distance to moon at apoapsis, except that we don't. Position at is going to be relative to the body that the thing is orbiting. So if we're calculating the position of the ship at a time and the position of the moon at a time, because they happen to be orbiting the same body, that's fine. If we were trying to do some sort of comparison of something that isn't orbiting Kerbin, though, well, then we'd have to figure out a different strategy. And one thing you could do is total up the difference in position of the thing and the thing that it's orbiting and the thing that that's orbiting, etc., etc. All right, our next bug comes from Mark Eisenberg, and this is less of a bug in the code and more of a bug with our strategy. So if you remember, when we initially started writing our script to transfer to the moon, the idea was we would look at the closest approach wherever on the orbit that happened to be and try and make that closest approach 0 meters and incrementally adjust our orbit so that it would slowly end up closer and closer and closer. And that's great. And that's what we ended up doing, and except that we couldn't do exactly that because, well, it's not a unimodal function and blah, blah, blah. What we ended up doing to sort of cheat is to say, hey, let's just calculate the distance to the moon at apoapsis. So we found the apoapsis and we said, okay, what's the distance to the moon at that point? But there's one problem with that. And let's imagine that so if we have an orbit like this and we're trying to say, hey, the apoapsis, the distant apoapsis here is fine, but is this an improvement? Well, yes, we can visually see our apoapsis is closer to the moon, and presumably if the moon doesn't move too far away, that's going to be true as well. So it makes sense if we're trying to slowly walk our maneuver node to a good position, we'll slowly increase it and increase it and increase it until we end up in a lunar encounter. But if we start searching here, well, then we've got an issue, because what's the easiest way to get the apoapsis, the position at apoapsis closest to the moon? Well, it's to decelerate, right? And that's in fact what this script does if you happen to try to find a good maneuver when we are on the same side of Kerbin as the moon. So that's a little bit of a challenge. Because it's not really a code issue. It's just that, hey, because of our starting conditions, we're not, the hill climbing algorithm doesn't have a gradient to climb on. In fact, it has sort of perverse incentives. But if we could somehow guarantee that we're starting looking at a maneuver over here, it's never going to say, hey, well, the most efficient way to get the apoapsis closer is to swing it back around. So we don't have to worry about it. If we can at least nudge it so that we're starting the maneuver at the right time. And so that's what we're going to do to fix this one. So just to make sure that we're able to test this fix, I've updated our main function. I say until false, turn off RCS, wait until wait until RCS. And until we don't have a next maneuver node, remove any maneuver nodes that may be on our flight path, and then try our do transfer function. So that way we can run the do transfer function over and over and over on our test craft so we can verify that this is working. So this is the function that we need to fix. We say, okay, we've got a transfer, we've got a candidate starting maneuver of 30 seconds from now, 0 delta V in any direction. We improve it based on the does it transfer to the moon or not-ness of it. Then we create the maneuver node, we add it to the flight plan. What we want to do is make sure that we're starting off our search at a reasonable point, because it has bad incentives if we're searching at a different point. So I'm going to say local start time, let's call start search time, is something. We'll do that. That's a to-do. And then instead of saying, actually, let's just pull this up here for now. Time seconds plus 30. We're just going to pull that variable out, because if we can get it to be something reasonable, well, then hooray for us. Then we should be able to search things just fine, regardless of when we happen to start looking. In the last episode, it just happened that we ended up on the far side of Kerbin from the moon, and so we didn't encounter it. But hey, if things had gone a little differently, well, we'd have been in trouble. So what can we do? Well, we already have a system. What we want to do is we could say, hey, we want to be on the far side of Kerbin from the moon. So what we want to do is just find the point in our orbit where we have a maximum angle with the moon, right? So, and we already have 2 algorithms that can, in theory, crawl up these things for us. So let's just use that. We have ternary search. Let's find the other ternary search. Ternary search. Let's just copy this as our sort of prototype. And we'll jump back into here and kind of rewrite this a little bit. This is finding our apoapsis time. Let's change this to start search time, and it's going to be ternary search, and it's going to try and find the maximum value of some function within a time window, within a minimum and a maximum input value, and to some degree of accuracy. So I'm going to say angle to moon. I don't know. That seems reasonable to me. We'll give it a start time of time seconds plus 30. And we'll say the end time is going to be time seconds plus 30 plus our orbit period. And comma. And we can leave this one, so find to within 1 second a time that has the maximum angle to the moon. And we have to write that function. Let's get rid of this search bar here. we'll go ahead and write that. And this actually isn't too hard for us to do. So angle to moon, and this is going to get some parameter t, which the first time it's called is going to be time seconds plus 30 or somewhere in there, and it's going to slowly whittle down until it finds the maximum value. We just have to return some angle. Well, we actually can get that by calling vector angle between two vectors. And what are the two vectors that we need? Well, the vector that is the ship's position at that time pointed toward Kerbin, and the vector of the moon's position at that time pointed toward Kerbin. So if we just say position at, and we'll say ship at t, and I'm going to say Kerbin position minus position at t, and then Kerbin position minus position at moon at t, then this is going to work. And it doesn't really matter if we're looking at the direction of whether we want to subtract Kerbin position or subtract the position of the thing. It doesn't matter, because if we're looking at the we care about the angle of the two, and as long as we're consistent, we should be fine. So let's go ahead and run this and see if it gives us a good starting point. Okay, so I have the craft kind of reset here, and if we take a look at the moon, where are we relative to the moon? I think this is a good example where, well, let's run it once from the far side and make sure that the condition that we tested before is just fine. And unfortunately, yeah, we can't time warp anywhere near as efficiently as we'd like. So this is the case that was already working. And if I go ahead and just hit RCS, it's going to go ahead, and it's already done. It's already figured out where the time is. We can tell because it's nudging the apoapsis. So it's already decided, hey, this is the best time to do this. And there we go. So that goes ahead and finds an encounter for us. I'll go ahead and remove that. And then let's warp ahead and see now if we end up on the near side of the moon, how that's going to be. I'm getting some... That's graphically a little interesting. Okay. So now, again, if we were trying to do this using the old strategy, the best thing it would do is it would say, hey, I need to bring my apoapsis closer to the moon. No problem. And it would burn retrograde. And that would be miserable. So let's hit RCS and see. See, now it immediately does the same thing. It searches to find the point where, hey, the angle is the maximum, and it's going to find about 180 degrees from where the moon is and use that as our starting point. And that means that we can use this hill climbing mechanism with impunity, because at that point, the incentives are working in the correct way. So thank you, both of you, for bringing up those problems. I'm glad we were able to get those solved, because we didn't encounter them the first time. Sure is important that we encounter them now. Okay, so with those bugs fixed, it's time for us to look at the end game. What I'm actually going to do inside our do transfer, well, we can uncomment this whole execute maneuver thing. We don't actually have to add the maneuver to the flight plan anymore. We had that there so that we could visualize it. But what I'm going to do is I'm going to say wait until body equals moon. And this is the current body that we're orbiting. So we're basically just going to chill until we actually get to the moon, and then wait 1 second, because the next step is going to be, well, to crash safely. Let's say do hoverslam, which is also known as a suicide burn. Basically, we're gonna be SpaceXing this, or any number of different people do similar, whatever. Let's find a nice place to start adding some code. We've got do shutdown, and that's at the very end down. Or actually, we have shutdown over here. Fair enough. Is do shutdown. Lock steering to burn. Okay. Okay, so we're going to add, a new function, do hoverslam. And the whole job of this function is to prevent us from crashing into the surface. So, believe it or not, this is not going to be too tricky. First thing we're going to do is we're going to lock our steering to SRF retrograde. Now, this is different from locking to prograde or retrograde. What we're doing is we're saying lock to retrograde using our surface velocity. So basically point the tail end of our craft at the ground, because, hey, we're going to need to thrust in order to do that. Now, the one thing that we're going to make heavy use of, and this is not my idea, but it's a lot cleverer than the stuff that I've written in the past, and so we're going to go ahead and use it, is we're going to use this formula called the stopping distance formula. And you'll see this a lot in terms of braking distance, which involves some friction and stuff. But basically trying to figure out how far, if you're traveling 30 miles an hour in your car and you slam on the brakes and the brakes can decelerate at such and such a rate, how far are you going to travel before you come to a complete stop? And this is similar to that. So stopping distance is equal to velocity. Well, I'm just going to say v squared divided by 2a. And so that's that. A being the acceleration, or in our case, deceleration. But we're accelerating opposite to the direction that we're going. So that's how that works. So this gives us the total distance that we would travel if we were to ignite our engines and try and brake as fast as possible. What we can do then is, we can adjust our code to just say, let's say we have some sort of percentage. Let's assume some more stuff. We'll do some more optimistic programming. We'll say lock percent. I'm going to just say PCT to, and we'll say distance to ground divided by, or actually I have that backwards. We'll say stopping distance divided by distance to ground. So we have to write functions to give us back those values, but that's going to say, okay, if it's going to take us 500 meters to slow down to 0 vertical speed, well, how close are we to that? Do we need to fire right away? Can we wait a little bit? Are we halfway through the distance it would take us to slow down? And we can then use that percentage to control our throttle. So what we're going to do first is we're going to say wait until percent is greater than 1. And this may seem like, hey, wait until we've already fallen too far. But you got to remember that our ability to brake, our ability to accelerate, is going to increase because we're going to be losing a little bit of mass. So it's okay for us to do this. This is going to give us a reasonable metric of, okay, now is the time when we want to start firing our thrusters. So we'll do that. Wait until percentage 1, and then we're just going to lock the throttle to that percentage. And then we've got a couple of simple things here. So when the stopping distance is, or actually no, when the distance to ground is less than 500, and generally I don't use when statements, but this would be a good example. We'll say gear on, or well, we can toggle gear. No, gear on is fine. I think that's been fixed. Then, okay, so we're locking throttle to some percentage, and presumably that's full throttle, but as our stopping distance, if we are managing to slow down and we have less of a distance to travel, then we're not going to be firing at full thrust. So we can throttle down a little bit and still end up in a good position. So then I'm just going to wait until the ship's vertical speed is greater than 0. So basically we've slowed down and now we're about to start thrusting back upward because we've managed to fully brake. Once we do that, we'll say lock throttle to 0 and unlock our steering. Okay, so how do we actually do these two functions? Because we've assumed there are two functions that we're going to need, and let's write them out. So function, let's start with distance to ground. Actually, yeah. Sure, let's start with distance to ground. And we don't get any parameter for this. We are going to take our altitude, but then we're going to subtract the height of the terrain underneath us. So we're going to say body geoposition of, ship position. Now what this is doing is it's getting the position of the terrain underneath us. So basically, if we're casting a shadow, if there's a light right above us, it's the part of the terrain where our shadow is. We're going to just, from that position, we're going to get the terrain height. I hope I spelled that correctly. We'll find out, I suppose. The last thing that we're going to need here, though, is we also need to subtract a radar offset. The radar offset has to do with the fact that when we're measuring our altitude, we're measuring it from the center of the, or from the, I think from the control of the craft rather than from the base of the landing legs. So that's not good. That means that we're assuming that our craft is a little bit offset from what it is. What I'm going to do is I'm just going to type in the number here. In theory, you could also measure this when the craft starts up or try and compute it via some other stuff, but we're just going to go ahead and say, okay, we're just going to deal with that as being sort of the offset from our radar because we're not measuring from the bottom of the craft. So we want the distance of our feet to the ground, not the distance of something else to the ground. Okay, and that's that one done. That's right, function stopping distance. And this one is a little bit more complex. Let's go ahead and grab our formula here. Well, I suppose we can take both of these. Okay, so the stopping distance, we need to know the velocity and we need to know our acceleration. Now, because we're crashing into the moon, we're pretty much going to ignore any lateral movement. We're going to presume we're falling straight down. The fact that we're steering in surface retrograde means that we're going to cancel out any lateral movement anyway, but when we're calculating how much thrust we'll need, we're kind of ignoring that. It'll end up working out, I hope. Okay. So what we need to do is we need to figure out this velocity, and that's just ship vertical speed. So we'll go ahead and do that. Then we need to divide that by 2 times, 2 times our max deceleration. There we go, deceleration. And we can return this. Whoops, period goes there. Ship vertical speed times 2 divided by 2 times max deceleration. Now, though that's assuming we have this variable, so we got to write that too. Okay, so let's write that. Local max deceleration is, and well, what is it? Well, we can do ship available thrust divided by ship mass. That is the acceleration, the deceleration that we can provide. Now, that's not quite correct, though, because we also need to factor in that some of our deceleration is going to be used up, effectively, just stopping gravity from speeding us up. So we need to subtract the amount of acceleration we're going to experience from the moon, from gravity. And we're going to cheat here. We could calculate gravity for our particular altitude, but honestly, it's 9.8 meters per second here, and I think on the ISS it's 9.6 or something. It's something very small. Obviously, if we were decelerating from a crazy high distance, it would matter. We're just going to look at the gravity at the surface of the moon and use that. But we can calculate that by just saying constant g times body mass divided by body radius squared. And that should give us the surface gravity on the moon. Then we just have to subtract gravity from our possible deceleration. And yeah, we'll just add some extra things just to make that a little clearer. We don't need to because order of operations, but that's great. So this should give us our stopping distance. We've got the distance to ground, and that means that what we're going to do is we're going to say, okay, it's going to take us, a kilometer to slow down to 0, and we've got 2 kilometers to go, so we don't fire in. As soon as we get to a kilometer away, though, then the percentage is going to be above 1. We'll throttle up to, well, it'll try and throttle to more than 1, but it's only going to throttle to 1. And then as we get closer, we lose some of our mass. We're able to decelerate faster than we even predicted. This calculation is going to continue to go because we're using this lock keyword. And so the stopping distance is going to go down. We're going to say, actually, we can slow down sooner. And so we only need to be, we're only some of the way there. So maybe it's, 0.8. And then our throttle is going to go down to 0.8. So we should be matching this pretty darn closely. And so barring any bugs, which I'm sure we will soon discover, we're pretty much good to go. Yep, the when syntax, you're supposed to have a then keyword before this curly brace. Let's fix that up. And hello, CheersKevin here, and the good news is that, we fixed up any bugs that we have in our code base. The bad news is that you're going to have to wait for one more episode to see us stick that landing. And the reason for that is that, we're unlocking the steering, and I happen to know, because I can see into the future, that's going to mean it's kind of hard to stay upright. Even if we slow down at exactly the right pace, if we're coming down and trying to have a velocity of effectively 0 when we touch the ground, well, it's likely that we can bounce and tip over if the ground isn't perfectly flat. Now, we're not going to spend a whole bunch of time trying to figure out how to land on ground that is perfectly flat, because that's a more complex question, but at the very least, we can try and use our stabilization to point us in a direction opposite to the terrain. So I want to add that in another episode. And then I'd also like to see if we can add, we'll walk through how to add some judicious time warping so that as you're running your own scripts, it doesn't take, I don't know, an hour and a half of real world time. Or you sitting around manually running things, because particularly for long missions, you want to be able to walk away from the computer for a bit. It takes a while. So we will wrap things up in the final episode, and I will see you next week for that. In the meantime, cheers.